tell the name and the topic, the title of your presentation. If you want to move around, you may do this. When you are ready, please tell us so we can start from now. 12, 13 minutes, guys. There's no need to talk for 1 hour. I think if you have something to say, you can say it in 12 minutes. It's okay. Dimitrios is our administrator of the website of the Hellenic Physical Society. Dimitrios is the administrator of Balkan Physical Union website. He rules everything. He controls the national competition of the Hellenic Physical Society. Let's say he's a great guy. Give him an applause. Okay. So when you are ready, Marina will start. Take your time. And when cameraman and Dimitrios said, we may start.
Good evening, everyone. My name is Marina Giannakopoulou, and I'm a rising 11th grader in Athens College in Greece. I'm here to talk to you about a project that I carried out the previous school year entitled Heisenberg's Uncertainty Principle, a first look at quantum mechanics and its extensions. Here's a quick overview of my presentation. Firstly, I'll introduce you to the project, its purpose and intended audience, and then I will give you an idea of the most important points. Of course, the presentation will be based on my work, but I will also be enriching it with some details that I had the chance to learn this summer at Brown University in the US. To begin with, this project was completed in the framework of the Middle Years program. It is a quinquennial international educational program that my school follows. At the end of it, each student is given the chance to conduct research, create a product, evaluate it, and submit a report on a topic of their choice. I selected Heisenberg's uncertainty principle, a fundamental concept in quantum mechanics which governs the very, very small things in our universe. My project is a 20-page document, and it sure is the outcome of research, but not just that. As I am sure many of you are, I too am interested in understanding how the universe functions and why it functions the way it does. So, how can we know? The answer is physics. And what is one of the most fundamental fields of physics studying this? Quantum mechanics. And then you say, perfect, quantum mechanics, and you get excited and you start exploring it and it's great, until these show up. And as my instructor at Brown, Dr. Umberto Gilmer, pointed out, you might then start questioning your knowledge. You understand what is missing. And you might even end up wondering about people, but let's not be too dramatic. In a less extreme scenario, someone seeing this math might just stop bothering with the topic. Especially for students of our age only having a knowledge of high school physics, it is particularly difficult to find books and papers both explaining advanced concepts and considering our level of knowledge. I'm sure many students are interested in understanding the physics of our universe. Some of them devote more time, they read, they encounter unknown concepts, they look them up, then other unknown concepts pop up, and they end up with loads and loads of tabs open in their computer. And somehow, they now have more questions than when they started, but at least they acquire better understanding. However, this is not the case for everyone. That is why I decided to create a document introducing in a precise and entertaining manner one of those advanced concepts, Heisenberg's uncertainty principle. Not only to help others understand as if I already knew, but also to help myself better understand, because I too was struggling. High school students are the main intended readers, yet anybody having similar knowledge of math and physics might want to read it. So, I've introduced a project about Heisenberg's uncertainty principle. But what is that? I think it's time to really get to know both that and what that document includes. Of course, I won't have the time to explain in detail everything that is included, but I will give you an idea of the most important points. Heisenberg's uncertainty principle was formulated in 1927 by German physicist Werner Heisenberg. It expresses a relationship between two measurable quantities, A and B. The important thing about those quantities is that they do not commute. What that means? It means that the order in which they are multiplied matters. A times B is not equal to B times A. In this case, we can define a quantity called a commutator. A commutator of A and B is equal to A times B minus B times A. And as you can see, if A and B commute, their commutator is zero. If A and B do not commute, their commutator is non-zero. There are several quantities which do not commute and for which the principle can be expressed. The most common ones are position and momentum. Remember that momentum is the product of mass times velocity. So let's move on to the definition. According to Heisenberg's uncertainty principle for position and momentum, exact values cannot be assigned to the position and momentum of a system simultaneously. These quantities can only be determined with some uncertainty. The greater the uncertainty for one quantity, the less the uncertainty for the other. And here, it is important to note that the uncertainty cannot be zero. The explanation for that is quite straightforward. We will only need to consider the general form of Heisenberg's uncertainty principle for position and momentum, which is this. Delta x and delta p represent the uncertainty in position and momentum respectively. Psi represents the state of the system, and between the two psi's you can see the commutator of x and p. Since position and momentum do not commute as we saw before, then their commutator is non-zero, which is why the second part of the inequality is non-zero too. And because it is also positive, as we will see later, delta x and delta p cannot be zero. You can also see the simplified version of the same inequality, where h is Planck's constant, a really small number approximately equal to 6.6 times 10 to the negative 34 joules times seconds. And here you understand why the second part is always positive. But is there a way to better perceive uncertainty and understand it? The answer is yes. There are different ways to approach this. Today, I will elaborate on wave-particle duality and wave functions. Let's begin with wave-particle duality. According to it, a particle can behave both like a particle and like a wave, which to us might seem strange, but it is true. As in the double-slit experiment, the wave-like behavior of a particle can only be observed after many measurements, and the wave-like pattern that is created shows the probability distribution for the position of the electron. In other words, it shows the likelihood of the electron having each value of position. So we understand that this wave is not a physical wave like a mechanical wave. It is rather a mathematical object. Specifically, it is derived from the so-called wave function of a system. The wave function is a mathematical wave too, and it describes the state of a system, such as what position it may have or its energy level. It is usually symbolized using the Greek letters psi or phi, and it has a general form which can be expressed using different bases. This way of expressing it is particularly useful when dealing with measurements. The most common bases are position bases and momentum bases, psi of x and psi of p respectively. Here, it is important to clarify that being at the position basis, for instance, doesn't mean that we can only examine position. We can examine momentum too, or some other quantity. The only difference is that we will have to express it in terms of position. To better understand this, imagine that the different bases are different languages that express the same wave function, like the same idea. So the only difference is the code used to do this. Returning back to what I was saying before, wave functions do describe the state of a system, but they are neither what we can measure nor what we see in the double-slit experiment. What we can measure is the probability distribution, which is given by squaring the magnitude of a wave function. And now that we have this new relationship, we can create the respective graphs. Here are some simplified versions with using the position basis just to better understand uncertainty. The trick here is that whenever you see a peak, you understand that the value of position is most probably somewhere around the peak. What about momentum? We will have to use the Broll hypothesis for that. It relates wavelength to momentum. So let's examine the first case. Even though the curve is quite large, we understand that there is a peak around the middle, which is why the uncertainty in position is not very large. But because there's only one curve and we cannot know the wavelength of this wave, the uncertainty in momentum is large. In the second case, there are many peaks of equal height, so we cannot know which is the most probable value for position. That's why the uncertainty in position is large. But because the wavelength is quite clear, the uncertainty in momentum is small. After having said all that, I'm sure there must be people thinking, all right, you've talked about Heisenberg's uncertainty principle. So what? Are there any applications? There sure are. And one of them relates to the Bohr model, the atomic model that Bohr introduced and looks like this. I'm sure most of you are familiar with it. According to the Bohr model, the atom consists of a positive core and electrons traveling around it at fixed distances. But even though this model is still used in some cases, it doesn't always depict reality, and we can use Heisenberg's uncertainty principle to show why. The problem with the Bohr model is that it suggests that we can know the exact position of the electron in terms of distance from the nucleus, and this violates Heisenberg's uncertainty principle. Using the principles inequality, we can find the minimum uncertainty in position for the electron, which you can see on the board. This uncertainty for position is greater than the diameter that the Bohr model suggests, the diameter of the atom. This doesn't only mean that the electron could be found outside the atom that the Bohr model suggests, it also means that it could be found somewhere between those fixed orbits. And that is why the Bohr model is inaccurate. In reality, the atom looks more like this. Actually, this is not exactly reality. It is a depiction of the possible positions that an electron could have in a specific state of the atom. In other words, it shows the probability distribution for position of the electron, and it is called an electron cloud. But since an atom can be in many different states, here is a more detailed depiction of the electron's position probability distribution clouds for the different states of the hydrogen atom. Now, remember I told you that all this is presented in an entertaining and friendly manner? That's because it is all written as a fun journey, where the reader has several friends who are athletes and provide real-life comparisons whenever possible. So I would like to end my presentation by reading you some extracts from the beginning and the end of my project to show you how that works. The quantum world. Think of everyday life. Imagine you were a skillful basketball player and you were about to shoot. You calculate the angle with which you will throw the ball and you are sure that you will make it. Everything seems perfect until a gust of wind blows the ball and you miss. You may be annoyed, but you are definitely not scared. This could have happened to any athlete performing ball sports. Nothing was strange, you just didn't consider all the variables. Otherwise, you would have predicted the path that the ball would follow. That seems rather straightforward, right? And it is, in the classical world, in the microscopic world where humans live. But you cannot say the same thing about the quantum world. Boom! Now everything becomes confusing. What do you mean I can't know which path the ball would follow? Keep calm. We will make this clear. And after making this clear, we end up here. Throughout our journey, did you ever wonder if the uncertainty principle is just a concept in quantum mechanics? Of course no, we would all say. All the time I was squeezing our brains to understand all that stuff. And it's true. So we can think about it now. Even though Heisenberg refers to a principle applicable on a scale which we do not perceive, we may draw conclusions about our life as well. Tennis player. Hey, we're here too. Stop philosophizing. I can't stand thinking about uncertainty anymore. Wait a second. Is it maybe this uncertainty that is stressing out athletes? Is it something different? Maybe for them, whatever is true about the world and can affect their performance matters, even if it is not perceivable in macroscopy. We may never know. However, a lot of them will most probably keep their rituals to concentrate and ensure that everything will go as planned. In this picture, you can see Rafael Nadal, one of the greatest tennis players, arranging his bottles, and he states, "This way, I make them the same each time so I can concentrate solely on the game and what lies ahead. Thank you very much.
Congratulations, Marina, for your great presentation and your accuracy. Omeros, are you ready? Please present yourself.
Wait 1 second, please. Okay. Hello everyone, my name is Homer Papadopoulos. I'm a 10th grade student in the Hellenic College of Thessaloniki, and my presentation is going to be about Thomas Young's double-slit experiment, how to recreate it at home, and why it is important. Additionally, I would also like to thank Banani Gem for editing this presentation, and I hope that you will enjoy it. So, in today's world, we scientists and students all want to improve quantum physics by searching for new information. However, we must not forget how we managed to get to this point and how it all started. So we're going to talk about the world's first ever quantum physics experiment and how it helped with the help of the scientists of the past shape our perception of the universe and physics forever. So, we need to start from something pretty simple. A single word. Light. So, you might be asking, what is light? Well, one could say that light is the spectrum of electromagnetic radiation that is visible to us, ranging from 400 to 700 nanometers. That's at least the textbook definition. And you are probably going to say that we already know that. So, let's ask a different question. How does light work? Well, the nature of light has been a subject of debate for centuries. The first one to work with light was Descartes, who assumed, although incorrectly, that light travels faster in denser mediums based on the way that sound waves work, thus reaching the conclusion that light functions as a wave. However, light has to travel through a medium, right? But what happens in space, where there is no medium since it's a vacuum? Well, for that, there were two theories that were the most prominent. The first one was the wave theory. Huygens had suggested that light waves travel through space, mediated by the ether, an invisible and weightless substance that exists throughout air and space. The search for ether was quite notable during the 19th century and before being disproven. It lasted until the late 1800s based on the evidence by Charles Wheatstone's proposed model demonstrating that ether carried light waves by vibrating at an angle perpendicular to the direction of light propagation, and James Clerk Maxwell's detailed models describing the construction of this invisible substance. The second theory was the particle theory, also known as the corpuscular theory of light, which states that light is made up of small particles called corpuscles, which means little particles, that travel in a straight line with finite velocity and possess momentum. Isaac Newton laid the foundation for this theory through his work in optics. This early conception of the particle theory of light was a predecessor to the modern understanding of photons. This theory came to dominate conceptions of light in the 18th century, displacing the previously prominent vibration theories, where light was viewed as pressure of the medium rather than between the source and the receiver, which was first described by Descartes and later refined by Huygens, while in part was correct and managing to explain successfully refraction, reflection, rectilinear propagation, and diffraction, it would fall out in the early 19th century as the wave theory of light amassed experimental evidence. And here we can see some depictions of the debate through art. For example, here you can see Newton and Huygens depicted as boxers, one of which sends through his eyes light waves, this one being Huygens, and Newton sending through his eyes particles. However, almost 100 years after both Newton and Huygens had proposed their theories, it was English physicist Thomas Young who would perform an experiment that strongly supported the wave-like nature of light. Because Young believed that light was composed of waves, he assumed that some type of interaction would occur when two light waves met. To test this hypothesis, he initially used a vertical surface containing a narrow slit to produce a continuous light beam containing waves that propagate in phase from ordinary sunlight. When the sun's rays entered the slit, they spread out or diffracted to produce a single wave. Secondarily, he allowed the light to illuminate a second screen with two closely spaced slits. In that case, two additional sources of coherent light, perfectly in step with each other, were produced. Light from its slit traveling simultaneously to a single point halfway between the slits and the second surface reached at the same time. The resulting waves reinforced each other to produce a much larger wave. However, if only one point is considered, one would say that the light from the distant slit would arrive after the light from the closer slit. So these two waves would be out of step with each other and might cancel each out, produce darkness, also known as gaps. Of course, today it should be noted that light presents both wave-like and particle-like properties. However, we're not going to analyze this in this presentation. And now we can say how you can create the double-slit experiment at your home. So, you're going to need for the construction a small sheet of thick paper, preferably a photographic paper, scissors, a tape, which is optional if you have other means of stability, a cardboard cutter, a laser, which can be found even in a presentation pointer like this one, a magnifying glass for precision, which is optional if you think you have great vision, and a stand for the laser and the paper, preferably made of wood or by aligning holding stands for stability and portability, which can be found in a physics lab or at home. But now, caution please. Do not use the laser by pointing it at someone's eyes, by not closing it when using it, by not placing it in a stable position where it can fall and accidentally be pointed at someone's eyes, or if you have a cat in the room. So now, we are going to set up the model. So you're going to need to make two parallel small incisions 1 millimeter apart from each other, or closer, if you're able to, using the cardboard cutter. You can also use the magnifying glass for precision and a ruler to make them parallel. Second, place the pointer in a stable place, like the stabilizer, as we said, the stand, in a way that the beam passes through the incision at a 90-degree angle. And please keep this in mind, because otherwise the results might be different. And third, you can use a piece of paper or a wall to display the result. And then observe. Here you can see the construction which I made for the experiment, which includes a laser, which is stably held by two pieces of metal, which I have put in a wooden plank. And also I have made a small construction to hold the paper in place, from which, as you can also see here, if you can see, there is a small slit, actually two slits, which will help us with the experiment. So now, let's observe. The light is spread out, but instead of a continuous line, it appears in parallel dots. Thus, This could mean that light is making a wave-like movements, indicating that it acts as a wave. So, as you can see here also, we have the result of the experiment that I personally did, and we can, through this way, reach the result that when light is passed through the incision, the beam spreads and becomes wider than expected. This important observation lends a significant amount of credibility to the wave theory of light. Like waves in water, light waves encountering the edge of an object appear to bend around the edges and into its geometric shadow, a region that is not directly illuminated by the light beam, since the middle part of the slit is covering it. The interference pattern also proves that the particle nature of light, even though that wasn't observed by Thomas Young himself in 1801, but rather was discovered as part of the photoelectric effect by Heinrich Hertz in 1887, and was also explained by Albert Einstein in 1905, for which he was awarded the Nobel Prize in Physics in 1921. And now you might be asking, what does that mean, that light acts as a wave? You might ask, can particles behave like that? Well, no, because if light consisted exclusively from classical particles, then the pattern size would depend on the size of the slit proportionately, and would essentially appear as the shape of the slit in the wall below us, behind us. However, as you can see, the opposite happens, and the beam is refracted towards the outside. Thus, it means that light cannot exist only as particles, and that it needs to exist as waves too. Thus, you might be asking, why is this experiment so significant? Well, as we said, the double slit experiment provided important evidence for the wave-like nature of light, and laid the foundation of quantum mechanics, which disproves the classical understanding of the world and dictates that particles can behave differently depending on how they are observed in a probabilistic nature. Thank you for your attention, and I hope you enjoyed the presentation.
Thank you very much, Omiros. Congratulations once more. Now let's move to our next presenter, Daniel Christovsky from North Macedonia. Daniel, please. I would also like to mention that Daniel won the bronze medal. Daniel?
Yeah, I did.
To the latest Balkan Physics Olympiad.
I'm Daniel Christovsky, and today I'll be presenting something that's not really connected with quantum physics, but rather the topic of electromagnetism in physics. The title is Lorenz's Force, Ocean's Course, Acyclic MEG Thrusters, Unmatched Source. So firstly, the topics here, just one moment. I need to turn something off. Yeah, here we go. 0. Right. That should be good now. So firstly, I will be talking what is magnetohydrodynamics as a topic of physics. What principle does it work according to? What led to this phenomenon? When did this phenomenon got firstly introduced? An overview of our work, how it was constructed, and is it used worldwide, as well as its advantages and disadvantages. So firstly, what is magnetohydrodynamics? Magnetohydrodynamics is a science that studies the dynamics of electrically conductive fluids, e.g. salt water, liquid iron, plasma, etc., anything that contains ions within its fluid. The word magnetohydrodynamics is composed of three parts: magneto meaning magnetic, hydro meaning water, or rather fluid, and dynamics meaning motion. A basic concept of magnetohydrodynamics is that magnetic fields can induce currents within the fluids and lead to an interesting interaction creating forces within those fluids. The fundamental force that is in this topic, it's the Lorentz force. So the Lorentz force, it's a basic force in electromagnetism, and it acts on charges moving at a certain speed. It requires a magnetic field to exist, and it's given by the formula Q times V times B times the sine of the angle alpha. Q is the charge of the particle, V is velocity, and B is the magnetic induction of the local field. And we can do a simple substitution for Q times V, where we take the time from the velocity and add it to the charge. And we know that current is defined as the amount of charge traveling through a certain area in a given time. And we will get the formula F that is equal to B times I times L times sine of alpha. This is just an animation of the Lorentz force, where we have the interaction of the magnetic field and the current, and we get the Lorentz force being produced. Now, the beginnings of magnetohydrodynamics are pretty interesting. Firstly, it was defined in a science journal in 1942 that was entitled "The Existence of Electromagnetic Hydrodynamic Waves." In a later edition, shortened the term to just magnetohydrodynamic waves. Now, there were more scientists beginning to explore this area, and a lot of people took interest in how to make use of this in thrusters. How do we make thrusters using this force for the sea travel or air travel? So, firstly, there was a prototype in 1966 where Professor Stuart Way built a 3-meter-long submarine that reached a maximum speed of 0.4 meters per second. Then a later improvement by the Japanese, which was of length 3.6 and reached a speed of 0.6 meters. And in 1991, the most significant and latest contribution was made, where there was a complete submarine built that carried a crew of 10 at a speed of 4.2 meters per second. Now, ion wind, the precursor of MHD, is the very idea that sparked the discussion on MHD. So ion wind is studied by electrofluid dynamics. That is just a sub-study of MHD, and it just depends on the current. Now, there are there is two steps on making ion wind. So we need two electrodes, one thin and one thicker, to direct the air. Charges accumulate most on sharp surfaces, so the thin electrode will be at a very high voltage, about 20 kilovolts. At that voltage, the air closest to the thin electrode begins to ionize, and in the dark we can see the light around the thin electrode, which is actually plasma or ionized air. So as we know from the Frank Hertz experiment, we are able to actually excite electrons and get some light. Ions whose charge is the same as the charge accumulated on the thin electrode are repelled upwards, creating a wind of ions that would move a structure upwards. Now, our prototype. We tested how we can bring this effect to submarines and most effectively eliminate noise pollution in the oceans. So, the part of electromagnetism is relatively little studied in schools. That is, the students' knowledge is not deepened. In doing so, they surf the net quite actively and come across unknown and unlearned terms and phenomena. So, our idea is a mixture of both. To learn more about something, you can't just sit and read a book or look at a video. It has to be interesting. It has to mean something to you. So that's why we created a project on MHD, which is inspired by project-based learning, which is very, very popular abroad in the European Union and America. Design. Coming across an example from YouTube, we used our existing knowledge of physics and designed a motor that did live up to our theoretical expectations. So here is a quick time-lapse of a 3D printing process. We used the 3D printer as it was the most suitable to create our prototype in the least amount of time and give us the best results. Now here is the demonstration. We use just food coloring to make the flow visible. There are 2 electrodes present, as well as 8 neodymium magnets that are able to generate the necessary components to create the Lorentz force. Now, is magnetohydrodynamics used in the world? Or if it is, where it is used? Sadly, nowhere. It is currently not used because this phenomenon has not been sufficiently researched. Theoretically, this phenomenon could also be used in space as part of the later stages of a rocket. Recently, in January of this year, a press release was made in a conference in which they explained their idea for a working rocket engine prototype by 2030. Now, the advantages. It's good that we have like a theoretical basis for this phenomena, but why would they actually use it over standard propellers or rockets with hydrogen and oxygen fossil fuels? So, firstly, the main advantage is actually elimination of noise pollution. So, if this technology is used in sea-based vehicles, it could just eliminate noise pollution as a whole. Propellers, due to their movement and vibrations, are actually generating a lot of noise pollution, which is detrimental to sea life. Now, another advantage is because this type of engine has no moving parts and it is able to generate thrust and rival propellers, it also makes construction of many vehicles easier, as well as it is also very easy to maintain because, again, no moving structures. And since this area of physics studies conducting fluids, this engine, again, could be used in rockets by using plasma as the main conducting fluid instead of seawater like in sea-based vehicles. Now, the main disadvantages during our testing of real-world scenarios, the most basic drawback was the presence of corrosion on the plates themselves. Due to some byproducts of half reactions in chemistry, we were not able to achieve 100% efficiency. Now, this can be very easily solved by using stainless steel plates, which are less resistant to corrosion, but still wouldn't achieve that 100% efficiency. The large magnetic field required for the motor to gain sufficient power is still a drawback because who can create a magnetic field that easily, except CERN. The large current required, again, due to the direct proportionality of the engine to the current supplied, is, again, a drawback. Again, CERN has already achieved this by making superconducting materials, and that was not possible for us. And the large presence of ohmic heating. Ohmic heating is not talked about that much, and it's a type of heating that occurs at the power unit. Because of the low resistance of the circuit, most of the power is drawn and is used on the power unit itself. And so, in the absence of resistance, the motor and in general the electric circuit is overheated. That would be all from me.
Thank you very much, Daniel. Congratulations for your presentation. Now I would like to ask Zoe Ketoudi to take the floor. Zoe.
Hello everyone, my name is Zoe Kitoudi, and today I'm really excited to share my presentation with you. So the topic of my presentation is called Quantum Physics in Medicine, from Theory to Healing. Firstly, let's say a few things about quantum physics. So, quantum physics is like looking at the universe through a magic microscope. It studies things so tiny like atoms, electrons, and light that the normal rules of nature seem to break. For example, light and other particles can be both waves and particles. It depends on our observation. Moreover, particles can be in two places simultaneously or even pass through walls. This strange world helps us understand modern technology. Now, let's combine quantum physics with medicine. Okay, we may not realize it, but many modern medical machines are based on quantum physics. MRI scans, PET scans, and even surgical lasers wouldn't exist without it. Also, understanding how atoms and molecules behave inside our bodies depends on quantum principles. So quantum physics is not just a theory. It is already helping medicine to diagnose and heal better. Okay. Let's talk about MRI. MRI stands for magnetic resonance imaging, and it is one of the most useful technologies in medicine today. Thanks to quantum physics, and specifically the quantum spin of hydrogen atoms, which are located inside of the human body, we have the ability to see inside of our bodies without using radiation. Let me explain you now how MRI works. Well, our body consists of 60 to 70% water, which means that it has a lot of hydrogen. So MRI uses magnetism and radio waves in order to align and activate these atoms, and afterwards records their response as an image. Through this innovation, we can access the inside of the human body without radiation, see organs and joints with greater precision, and of course make timely and correct diagnosis, thus saving a person's life. Let's continue with, have you ever had an MRI? If not, this is what it looks like. First we have a heart MRI, then we have a brain MRI, and lastly, a spine MRI. Okay, now let's continue with the PET scan, antimatter in the service of medicine. PET scan stands for positron emission tomography. It is a special machine that allows doctors to see how our body works on the inside. It doesn't just show what an organ looks like. It shows if it's working properly, if there's a problem, or if something like cancer is active. But how does a PET scan actually works? Well, a small amount of special medicine is a radioactive tracer is given to the patient. This medicine releases positrons, tiny particles of antimatter. Let me stay here for a second. Antimatter is like the mirror of matter. Every particle has an antiparticle with the same mass, but the opposite electric charge. So the positron is the antiparticle of the electron. It has positive charge while the electron has negative. So when the positrons meet the electrons inside of the human body, they destroy each other, they disappear, and afterwards they release energy. The PET scanner detects this energy and creates an image of what is happening on the inside. So doctors can see the tumor is active, how the heart is functioning, or how the brain is working. the quantum physics, the quantum medicine of tomorrow. Quantum physics doesn't stop with the machines we have today. Scientists have already started building new technologies like quantum sensors, which can measure heart activity and brain signals with incredible precision. In the future, medicine will become more personalized, meaning each patient will receive the treatment that fits them the best. Quantum physics gives us hope for more accurate and powerful diagnoses and treatments. Okay. Making the invisible visible thanks to quantum physics. Quantum physics, the science of the smallest particles in the universe, is becoming a powerful force in modern medicine. Although its rules may seem strange, they have led to amazing breakthroughs in how and they have helped us to understand better the human body. Thanks to quantum principles, new tools allow doctors to diagnose diseases with greater precision and often without the need of invasive procedures. From imaging machines to advanced sensors, quantum technology is helping to make medicine smarter, faster, and more personalized. What once sounded like science fiction is now a life-saving reality. Quantum physics is not just about theory, it's about unlocking new possibilities in healthcare and making the invisible visible. Let me end my presentation with a quote. Quantum physics gave us the tools, medicine gave them purpose. Thank you very much for your attention.
Dear colleagues, dear students from all the Balkan countries, we have the pleasure and honor to have with us the Deputy Mayor of Education, Mrs. Efi Theodoraki. It is a great honor to welcome you to this year summer school of the Balkan Union of Physicists. Your presence here highlights the importance of this event and your commitment to promoting education and scientific collaboration in our region. Thessaloniki, with its rich history and vibrant academic and research environment, is an ideal place for the exchange of knowledge and ideas. Your contribution to the organization of this event is truly valuable, and we would like to thank you for your support. We look forward to hearing your greeting and participating in this significant educational experience. Thank you very much, and we wish you every success in your work. Please come to the stage for a greeting.
Dear students, on behalf of the Mayor of Thessaloniki, Mr. Stelios Angeloudis, I welcome you to this extraordinary festival where science meets wonder. Today we celebrate not only human creativity, but also the mysteries of the universe through the lens of quantum physics. May this festival ignite curiosity, spark conversation, and open minds to the beauty of both science and culture. Together, let's explore the quantum world and celebrate discovery. The light here doesn't help me. Our municipality supports the Balkan Union of Physicists. It has responded and placed the event under the auspices. It has currently provided this hall to the organizers. We hope that our collaboration will continue. The municipality of Thessaloniki will support similar initiatives in the future. Thank you very much for the invitation, and I hope to see you again next year.
Thank you very much. Thank you very much. Please, Effie. Thank you very much. So, Effie, δεν καταλαβαίνω τα γράμματα. Αποστολοπούλου. Please to the stage.
Maybe to make full the PowerPoint. No. Maybe F5. Okay, thank you very much. I'm Evi Apostolopoulou, and I will talk to you about the contextuality and specifically the Cohen-Speicher theorem. So let's begin with the central question: do measurement outcomes reflect pre-existing properties, or are they defined by the measurement context? In quantum mechanics, contextuality is the claim that you cannot assign outcome values to all projected observers in advance, in a way that is independent of which other compatible observers are measured alongside them. The Cohen-Speicher theorem makes this precise. In Hilbert spaces of dimension 3 or higher, non-constant hidden variables assignments are impossible. So I'll show you how this is true. So I'll be quick with this. The goals of the presentations are firstly to clarify what I mean with saying contextuality, Cohen-Speicher theorem, you know. Secondly, to better to place it within the border shift from specific realism to quantum theory. Third, so what well contextuality is not just a foundational puzzle, but a resource that enables protocols beyond classical capabilities. Fifth, point out near-term directions, how these ideas guide experiment design and quantum architecture. So what is contextuality? What am I talking about? Contextuality is the property that a measurement outcome cannot be regarded as revealing a pre-existing context-independent value. Formally, there is no global value assignment to all the projectors that is consistent with the functional relations among computing sets. So, think of an observer A that can be jointly measured with B or alternatively with C. Quantum theory allows AB and AC to be competitive contexts, yet forbids assuming that A carries one fixed value across both contexts while perceiving an algebraic context. Why more than 3 dimensions? So, in 2 dimensions, the geometry is too simple. From three upwards orthogonally relations for contractions for any non-contextual assignment. So, this is not about experimental disturbance. It is a logical geometric feature of the Hilbert space structure. Classical realism took properties to exist independently of how we prove them. Laplacian
determinism as its core, the quantum revolution broke the template. Quantization, superposition, and the Bohr rule introduced intrinsic probabilistic structure. So, conceptual shocks followed, uncertainly the EPR argument for incompleteness and Bohr's reply measurement context is inseparable from meaning. Hidden variable programs attempting a rescue. Bell's theorem showed local realism is untamed. Cohen-Specker goes farther. Even dropping locally non-existent false. There is the pivot from classical objectivity to quantum contextual meaning. Rapid timeline. 1900s quantization. 1925 formalizations of quantum mechanics. 1935 EDR and Bohr's reply. 1952 Bohm's hidden variables. 1964 Bell no local realism. Bell no local realism. Cohen and 1967 Cohen-Specker no non-contextual realism in more than 3 dimensions. In the 2000s, the perspective Phillips contextuality is reframed as a principle and later as a result for quantum information. That is the trajectory that we ride for the remainder of this talk. Cohen-Specker, why context matters. Here is the core geometric idea. Observers correspond to projectors, compatible observers from context, mutually computing sets whose projectors sum to the identity. A non-contextual model would assign each projector a defined value, perceiving these relations in its context. Exactly one projector is one and the rest is 0. Functional relations among computing operations must hold under the assignment. Cohen-Specker constructed finite sets of project C3 and above with orthogonally graphs such as no assignment can clarify those contrasts simultaneously. The contraction is state independent. It does have no replay on statics or on entanglement, only on the structure of measurements. So, the formal statement stripped it into the essentials, assumptions. Consider Hilbert space H with more than 3 dimensions. Represent yes-no measurements by projection operators and non-contextual hidden variable models assigned to every projector P a value such that a functional composition and context normalization. You can also see here coincidence and etc. So this is specifically the theorem. Let me illustrate with a state-independent contradictions. In multi-qubit systems, the Peirce Mermet square arranges 9 observers into 3 rows and 3 columns. Quantum mechanics imposes that the product of operations along each row and the alum equals +1 except one light where it equals -1. A non-contextual assignment would require +1 that multiplied to those the same constraints, but multiplied all row constraints, all common constraints, whilst +1 and -1 simultaneously a logical impossibility. This captures the Cohen-Specker spirit, so no global contextuality value map we can exist while perceiving the operator relations. So, I'll be quick with this. Historically, contextuality we read as a paradox and oddity of the formalism. the modern view promotes it into a principle. You cannot model quantum predictions within any framework that assigns fixed concept-independent properties. The principle is powerful because it identifies what classical models cannot do without exponential overheading. It explains why certain interference and and compatibility patterns are exclusively quantum, turning into contextuality into a diagnosis of how quantum a project truly is. In computation, we now understand that contextuality underpins quantum advantage. Clifford circuits alone are clarified simulable. To reach universally, you inject magic states, and non-classically power of these states is tied to contextuality. In communication and cryptography, contextuality supports device-independent reasoning. If outcomes cannot be pre-programmed, non-contextuality, then certified randomness and certain security guarantees follow. So, the narrative flips from limitation of realism to an enabler of protocols that no classical machine can match. Contextuality is not confirmed to Blackboard. In inequalities and witnesses, analogous to Bell, no one can drive non-contextually inequalities that any non-contextual model must satisfy. Quantum systems violate these bounds. So, photonic interference trapped ions and superconducting qubits have all demonstrated state-independent contextuality with careful control compatible measurements. These experiments close to the loop. The Gaussian-Specker insight is physical. It shows up as measurable constraints on what any classical and non-conceptual descriptions could produce. That validates contextuality as a principle and a design guide for quantum hardware and protocols. So, and now to the future, 3 short directions. First, build contextuality witness directly into calibration and benchmarking of quantum devices. Treat contextuality as an operational resource to be quantified and not just inferred. Second, explore architectures that deliberately, orchestratedly, compatible contexts that amplify computational power. Third, push beyond quantum advantage narratives. Contextuality hits at new logics of inference, potentially relevant to complex systems and learning. The theme is simple. Yesterday's paradox becomes tomorrow's engine. And now I'm gonna close with this quote of Niels Bohr. Anyone who is not shocked by quantum mechanics has not understand yet. It isn't to the topic. And yeah, thank you. That was my presentation. I hope you enjoyed it. And yeah, thank you.
Congratulations, Evi. Thank you very much. Anya and Alessia, are you here?
Okay, hello everyone. I am Alessia and I'm from Albania.
Hello everyone, my name is Anja Mehmetas and we are students from Albania. I'm 16 years old and I study at Cemal Stafa High School in Tirana.
Our presentation today for you is Schrödinger's cat, a journey through quantum physics using a famous thought experiment. So firstly, who was Erwin Schrödinger? He was an Austrian theoretical physicist and one of the founding fathers in developing of the quantum mechanics. In 1926, he is well known for Schrödinger equation. This equation is central to quantum mechanics. It introduced the concept of the wave function, which represents the probabilities of a particle position, momentum, and other properties. In 1933, he won a Nobel Prize in physics. And then, in 1935, finally, Schrödinger's cat, the experiment which we are going to explain today.
So, what is Schrödinger experiment? Schrödinger's experiment is a thought experiment designed to illustrate the concept of superposition in quantum mechanics. Imagine placing a cat inside the sealed box along with three elements. First, a radioactive atom with 50% chance of decaying within 1 hour. Second, a Geiger counter which detects radiation if decay occurs. And third, a vial of poison which is released if the detector is triggered. If the atom decays, the Geiger counter activates, the poison is released and the cat dies. And if the atom does not decay, nothing happens and the cat stays alive. Until we open the box, the cat is considered both alive and dead at the same time, existing in the superposition of states.
So now imagine, we are back in 1935. Schrödinger put a cat in the box. He also had a radioactive nucleus in the box, and if it decays, we'll release a poison that will kill the cat. So the cat is either dead or alive, depending on either it decays or not. So we can't have an answer until we decide to open the box. So what Erwin Schrödinger calls the wave function is a big ensemble of two universes. In one universe, the cat is alive, and in another parallel universe, it is dead.
But now we have an illustrated experiment. So, imagine flipping a coin, but not checking the result. Until you look, the coin is both heads and tails at the same time, a blend of possibilities. In quantum physics, particles or entire systems can exist in multiple states simultaneously until measured. Schrödinger's cat brings the idea to the microscopic world, where it seems absurd. How can a cat be alive and dead at the same time?
You can try by yourself by creating a rolling dice with 3 pictures of the cat when it's dead and 3 pictures with the cat when it's alive. Now you can roll the dice and the probability is the same, 50% alive and 50% dead.
But why do we choose this topic? We choose this topic because it's not only scientific but also philosophical and deeply thought-provoking. It helps us explore some of the core mysteries of quantum mechanics. Schrödinger's cat raises fascinating questions like what truly is reality and is it independent on our observation?
You can understand it more easily from other phenomena by comparing it with different examples, as we did. It connects the science and philosophy in a unique way. It deals with the concept of objective reality. Does something exist in a certain state without being observed?
Let me end our presentation with conclusion. From this experiment, we learned 3 key ideas. First, quantum superposition. Until it is observed, the atom can be in both states, and therefore so can the cat, alive and dead. Second, the measurement problem. At that point, does really decide on a single outcome? When the atom decays, when the poison is released, or only when a human observes the cat? This highlights the role and the observer in shaping reality. And third, criticism on the Copenhagen interpretation. Schrödinger introduced its paradox to show the absurdity of applying quantum mechanics to everyday objects. He wanted us to question whether it makes sense to think of something microscopic, like a cat, and as the cat being both alive and dead at the same time. In conclusion, Schrödinger's cat challenges our understanding of reality, measurement, and the boundary between quantum mechanics and the world we experience. Thank you.
Thank you all.
Thank you.
Thank you very much, Anya and Alicia. Now let's move on to the Srina Vukcevic from Montenegro.
So, hello to everyone. My name is Srna Vukcevic. I am from Montenegro and I am a student at high school and gymnasium Slobodan Škerović. And today I will talk about quantum physics in general, what it is, how was it discovered, and some of its basics. So, let's start with what is actually quantum physics. Imagine, for example, taking a microscope and zooming deeper and deeper into the world. We will first of all see molecules, then atoms, electrons, protons, photons, and particles that are even smaller than that. But when we come to that level, the world doesn't work the way we expect. And that is where quantum physics comes in. Quantum physics is a branch of physics that studies behavior of matter and energy at the level of atoms and subatomic particles. So, how was it discovered? Until the early 20th century, Newton mechanics and Maxwell's equations of electromagnetism perfectly described the world. But at that period of time, there came some experiments which couldn't be really explained by classical physics. One of the most famous problems of that time was ultraviolet catastrophe, which started when physicists began to study black body radiation. A black body is a perfect emitter and absorber of heat. So, the actual phrase ultraviolet catastrophe actually refers to Ryle-Jean's law being proven wrong. Ryle-Jean's law is an approximation of spectral radiance of electromagnetic radiation as a function of wavelengths from a black body at a certain temperature. So, ultraviolet catastrophe refers to that Ryle-Jean's law being proven wrong when we talk about lights that have long wavelengths, but when it came to shorter ones, it didn't make sense. By this law, when we talk about lights with shorter wavelengths, the amount of energy that would increase in that time would be infinite. And that, of course, didn't make sense. In other words, a black body would emit an infinite amount of energy when entered the ultraviolet and blue light spectrum. And by this experiment, scientists didn't discover that Ryle-Jean's law was wrong. It was actually completely true when we talk about classical physics. And they discovered that at this problem, we have to look from a completely different perspective. That is when, in 1900, Max Planck discovered that energy is not continuous, but comes in small packets called quanta. And that was a revolutionary idea which contributed to quantum physics being born. Of course, this was not the only moment that was really important for quantum physics in history. We also have photoelectric effect, where Albert Einstein in 1905 discovered that when an atom hits light comes in discrete values called photons, and when a photon hits a metal surface, it ejects an electron. And this couldn't be explained by wave theory of light. We also have atomic spectral light, where in 1913, Niels Bohr proposed a model of an atom where he explained that every electron has its own specific energy level, and when it jumps from one level to another, it absorbs or emits a specific amount of energy. And double-slit experiment, where Thomas Young discovered that some particles, like electrons, produce interference patterns, but when we observe them, they act as particles. So, some fundamental ideas of quantum physics. First of all, we have quantization, where energy is not continuous but comes in small packets called quanta. Wave-particle theory, light and matter can behave both as waves and as particles. Uncertainty principle, where we cannot precisely say both velocity and a position of a particle, and more we know about one, the less we know about the other. and probability instead of certainty. In quantum world, we can say the exact location of a particle. We can only calculate a probability of it being in a certain place. So, quantum world is strange, but why is that? In quantum physics, there are some theories that in normal world make no sense. First of all, a particle can be in multiple places at the same time, which is called superposition. We also have quantum entanglement, where two particles can be connected regardless of their distance, and observation affects the outcome of an experiment. And even though these sound really strange, they were proven multiple times by so many experiments. Now, how can we apply such strange ideas and principles into everyday world? We actually apply them more than we think, because a lot of things that we're surrounded by couldn't be made without quantum physics, one of which being lasers. We also have MRI scanners, which are used to look into human body, solar cells, which are used to convert solar energy into electricity, electronics, because transistors could not be made without quantum physics, and last but not least, quantum computers, which there are made some of them, but they're still in development. And quantum computers are said to be machines that could do things that no supercomputers can do nowadays. So, quantum physics teaches us the nature on the smallest scale and doesn't follow our common sense intuition. It reveals an invisible layer of reality governed by new, exciting, and mind-bending rules. And for the last few days, we were talking about quantum physics, but what we can say is that it's not just physics of small particles, but it's also physics of limits of our understanding. Thank you.
Thank you very much, Irina. Your lecture was small, but it's very concrete. Thank you very much. Now let's move on to Bogdan Banovic. Bogdan, are you here?
So, good evening everyone from me too. My name is Bogdan Banovic and I come from Montenegro also. And today I'm going to talk about a little bit for the double slit experiment. First, before we move on, let us imagine this scene. We are in front of us, there is a wall with two slits in it, and behind it there is a screen that would record where those pebbles land. No, sorry. And behind it there is a screen that will record where the pebbles land. We are throwing at those wall with our double slits either pebbles or sand or something like it. So, when we do that, at our screen we are expecting to see two bands, and that is what we get. But now, what if we do it with our photons? So here is where our story begins. This experiment was firstly performed with light in 1801 by English polymath Thomas Young. It involved shining beam of monochromatic light at our wall with two parallel slits. And as we said, instead of seeing our expected two strips to correspond with the two slits, we see an interference pattern. So this is our expectation. But instead, here is what we get. So an interference pattern, which is behavior of waves. And in real life, it would look something like this. We actually can do double experiment at our homes. What we need is a laser and something like an aluminum foil or a carton board, which we can place like 2 13 to from to 20 to 30 centimeters from our laser, make two tiny vertical slits in it, not separated more by 1 millimeter, and a screen behind where we'll see the interference pattern at a distance at 1.5 meters from our double slits. So, as we said, this is what we get. And why this happens? We said this is a behavior of waves. So, this happens because of interference. There is constructive interference and destructive interference. The constructive interference is where we see those light bands. So what happens here is that the tops and bottoms of two waves meet in such a way that they create a resulting wave of a bigger amplitude. And a destructive interference is those our dark spots, those dark bands, where the tops of one wave and the bottoms of the other wave meet, that they cancel each other out. So now the question is light a wave or particle? And the answer is both. That is the dual nature of light, and not just light, but matter also. Yes, but matter also. So physicists tried recreating, doing the same experiment with other particles, in this case electrons, and what happens is there's again an interference pattern that we see on our screen. Even if we fire those tiny particles one by one at a time, we still see the interference pattern, just like with the waves. But how can an electron, as a particle, interfere with itself? Is if it passes through both slits at the same time. So what physicists try to do is to peek at the experiment. They placed a measuring device which would record where through what slit the electrons pass through. And what happened is a shocking result. The interference pattern disappeared, and instead we saw our two regular strips. So we come to the conclusion that the very act of, to say, observation affected the outcome of our experiment. So what does this teach us? That it teaches the fundamental of quantum mechanics, that the matter particles can behave like waves. That is the particle-wave duality. And that we cannot separate the observer from what is observed. The act of observation changes the outcome. And that the rules of classical physics break down when we look at things at the quantum scale. And last, for the conclusion, is that the double-slit experiment is more than a scientific trick. It's a window into a world where different rules apply. It teaches us that our initiative understanding of the universe must sometimes yield to experimental evidence. And I will end it all with a quote from a physicist, Richard Feynman, that said, "The double-slit experiment is absolutely impossible to explain in any classical way, and has in it the heart of quantum mechanics. In reality, it contains the only mystery." Thank you for your time.
Thank you very much, Bogdan. Umut Chakar, are you here? Umut? Please.
Can I have some help with the Greek alphabet? Oh. I need help with it. Yeah, I'm sorry.
We don't have internet. We need
Yes, don't we have he told me, don't we have internet access? If we don't, it's not a problem for me.
In order to prepare it, can you present it later? In order to put the Wi-Fi?
I can present it without the presentation too, if it's necessary. I think there's internet access.
Ah, okay.
Yeah. Okay. Can you help me with the slash symbol? I'm trying to. Is it this one? Oh, okay. Thanks. Now it shows. Okay.
Okay, so I'm Umut Çakar from Turkey, and today I will steer away slightly from quantum mechanics and take you for a walk back in classical mechanics, where I will talk about the implementation of a technology that can truly transform communities. Before starting, I would like to thank my mentor, Dr. Navarro from MIT Engineering, and the dear audience for their kind attention for listening to me. So, first of all, I find it necessary to talk about my motivation for doing this research. So I will talk about two terms, bio-inspired engineering and earthquakes. Bio-inspired engineering is basically observing biological systems like animals and mimicking their structure to build technologies that can outperform the conventional approaches. So for background information, I grew up in Turkey, and my community is one that is highly vulnerable to earthquakes. And when growing up, seismic events really disrupted my hometown, and I've seen many buildings collapse and the tragedies that came with them. So, distinct thing to know about earthquakes is that the first 24 hours are really critical, and it's the golden opportunity for localizing victims that are under the debris. So, today I will talk about this. For simplicity, I will refer to this as a snake robot, and how the motion strategies associated with them can help us find survivors faster. So, this is a robot that is composed of subsequent joints, 12 degrees of freedom, and it's basically a narrow tube that can navigate through cracks in earthquakes, in buildings under earthquake. So, I will not tire you with the exact mathematical implementation, but we can think of two motion types here. One is in a single plane, the wiggling motion we are all accustomed to, and one uses two sine waves that are perpendicular to each other, offset by 90 degrees phase. So you can think of it as a snake that lifts its belly and uses its tail and head to just push itself over. So the two post-earthquake search and rescue tasks we will investigate together are first this bumpy ramp, which is built in a simulation environment using flat and inclined segments to create discontinuous localized interruptions, and this height-filled terrain, which shows us a gravel environment that represents the collapsed debris after an earthquake. So, when we look at this environment, we see that it is tricky for normal robots to operate on them. When we think about like the MIT Minispot, the dog robot, you might know it as, or the wheeled robots or legged robots, they can navigate these places because it's really hard to find pivot points to enable stability. So these robots emerge as a promising technology, and I wanted to make a research by myself to see if there are any trade-offs involved in regarding agility, stability, energy efficiency, and also time of failure or success rate. So, as I share my findings, I will also like to talk about the intuition behind the findings. So if my friends are interested, they can maybe find any mistakes in my study, or they can expand it later further in the future. So, when I did the study,
my method was to conduct 20 controlled trials in both of the simulation environments for 30 meters. The names of the motion methods are lateral undulation, which is the 1D sine wave motion, and side bending, respectively. The first motion method is commonly used by all snakes around the world, as it's known to be more generalized, whether side bending is used by snakes in desert environments, as they take advantage of low friction terrain. So, when I was first starting this research, my intuition was that the 1D motion type would succeed in this rather flat terrain, whereas the second motion type that could lift itself would succeed in this bumpy terrain, but I was wrong. What we see here is that the motion type, the side bending, which utilizes 2D motion, can overcome these bumps better. And this helps in scenarios where you have to go from one floor to another and to ascend or descend to find earthquake survivors. Whereas our lateral undulation gate, which can wiggle, can navigate through these cracks and use the side surfaces as a grip to further propel itself through the channels. So here is a table which is rather obscure, so I will summarize the results. What I have seen is that the energy used per meter in the first lateral undulation method was significantly higher compared to the 2D motion. And this is rather, again, counterintuitive because it's a 1D motion instead of 2D. But the basic reasoning for this is that as you increase the ground contact, you experience more friction forces, which reduces the mechanical efficiency of the system. And the trade-off involved here is that even though it used more energy, it was more stable, and it was faster. For the second motion type, what we saw is that it has a problem with distributing the mechanical loads efficiently. So this means that you have to replace some parts of the robot again and again and again because they experience more ground contact more frequently compared to the others. So the motion types are inherently different and are clearly separated. Whereas one uses energy efficiency, it lacks stability and more reliable navigation. So upon finding these results, what I followed up is that can we use steering navigation to compensate for the problems that these gates experience? Gate is a motion type, to clarify, and I've seen that using sharper navigation angles, more abrupt changes, can compensate for this stability problems of the first motion type, and using a pivotal rotation technique, which I will further explain, allowed the second motion type to travel more reliably. So, for the specific implementation of the second motion, you can think of it basically as two sine waves, the ones we discussed together in this physics conference. You can think of two sine waves in superposition, but in perpendicular planes. When you move the lateral wave part of one side of the lateral wave faster, you get a rotation in the other axis. You can think of it as a rod, and if one of the rod's ends moves faster, you get a contralateral rotation. Another way of thinking is that instead of making one part go faster, you can stop the other end and make it rotate around that one. I have never seen an implementation of this rotation synthetically and in my research of other universities, but doing this allowed my robotic system to overcome any directional interruptions, and the success rate jumped from 30% to over 70% in my simulated trials. Currently, I'm building the hardware robotic system and introducing an AI agent to fix localized disturbances. However, I don't have fancy visuals today, so I won't be able to share it with you. So, what I would like to extrapolate and connect today is that knowing physics allows us to not just push in the microcosmos, but also build technologies that can help us improve all aspects of our communities. And I tied physics with my passion of bioengineering, bio-inspired engineering, and robotics control. So I hope that everyone can find a team in their life where they can merge physics within. Thanks for listening to me. It was an awesome experience for me.
Thank you very much. Although you didn't have a PowerPoint, your presentation was magnificent. Now let's move on to Stavros Karabassis. Stavros.
So, good afternoon, everyone. My name is Stavros Karabassis, and I'm a student here in Greece. Today, I'll present you my project with the title, Stellar Remnants and Quantum Mechanics, Bridging General Relativity and Quantum Physics. To begin with, I would like to introduce some fundamental concepts of general relativity. General relativity is based on the premise of the following equation. This equation expresses the equivalence between Einstein's tensor and the energy-momentum tensor. The part within the brackets has no physical meanings, so it's written in gray letters. Now, the point here is not understanding what tensors are, but the point here is understanding their physical meaning. Einstein's tensor represents the measure of space-time curvature, and the energy-momentum tensor represents the energy and momentum gathered in a specific place. Therefore, the above equation states that space-time geometry and curvature equals mass and energy. In other words, wherever there is matter or energy, space-time is curved. According to Einstein, gravity is the manifestation of a curvature of space-time. This means that gravity is a result of curved space-time and therefore a result of the presence of matter or energy. Compactness and intensity of space-time curvature. In order to set a curvature index, we need a relative measure, in other words, the ratio between two quantities. One quantity must show how intense gravity is, and therefore it's related to the mass of an object. The other quantity must show how this mass is distributed in space, and therefore it's related to the object's dimensions. Einstein's equations provide an enlightening view on this matter. Einstein's general relativity provides this equation that states that the relative intensity of space-time curvature depends on its compactness. The compactness is this specific part of the equation, m over r, which is the object's mass over the object's size. As you can understand, if the object mass becomes greater, the curvature of space-time becomes greater as well. In other words, the mass is proportionate to the intensity of space-time curvature. On the other hand, if the object's radius gets smaller, intensity becomes greater once again. The full understanding of stellar remnants requires a full understanding of their formation process in advance. For this reason, we must begin this journey to grasping the greatest wonders of nature, starting from stellar nebulae. From nebulae to protostars. A nebula is a region in space where significantly large amounts of gases such as hydrogen and helium, as well as dust and other elements, are concentrated. Nebulae can be distributed disturbed by multiple factors, most often supernova explosions. Such a disturbance causes instabilities in the nebula, since it affects the distribution of mass in it. So, if a part of the nebula collapses under its own gravity, it will concentrate more mass from its surroundings and compress it. The more matter is concentrated, the stronger the gravitational field will become. In this way, the large concentrations of mass create a very dense object, a protostar. As the protostar becomes denser, its temperature increases as well. From protostars to stars. When the object's temperature reaches 10 million degrees Celsius, the thermonuclear fusion of hydrogen into helium is triggered. Specifically, under such circumstances, atoms are compressed together until the nuclei combine. This happens because atoms vibrate intensively in high temperatures. And since they oscillate intensely, the repulsive force between the positively charged atoms reacting with each other is overcome. In the beginning of a star's life, it combines hydrogen to create a helium-4 atom. The mass of the helium atom is slightly smaller than the aggregation of the four hydrogen atoms. This small mass deficit is released in the form of energy, as predicted by the equation E = mc squared. A star that undergoes stable fusion is called a main sequence star. Our Sun is also considered in this category. Hydrostatic equilibrium. As a result of fusion, a balance is maintained between the star's gravity and internal pressure. In other words, while the star's own gravity tends to crush it, the pressure and heat from the core prevent this. However, at some point, the helium runs out. So the star will start to shrink under its own gravity. In this way, the pressure from the core increases, and consequently, the star expands again. At this point, the star's mass and temperature required for helium to be converted into higher elements. Sometime helium will run out too. A star less massive than 8 to 10 solar masses will start to shrink. During this process, the star exhibits an instability between its outer layers and the stellar core. In this way, the outer layers explode. As a result, the outer layers create a planetary nebula, and at the center of which there is a star called a white dwarf. Now, so far we have mentioned all this to conclude to electron degeneracy pressure. Inside white dwarfs, thermonuclear fusion does not occur. The balancing of the force of gravity is due to a quantum phenomenon. In this phenomenon is the degenerate motions of electrons, or electron degeneracy. Electron degeneracy is a result of Pauli's exclusion principle. This principle of quantum mechanics states that two fermions in the same system cannot have the same quantum state. Now, fermions are particles such as electrons, protons, neutrons, quarks, and many others. That is to say that they cannot have the same values in quantum numbers. Quantum numbers are the energy level, represented by n, the orbital type, the orbital orientation, and the spin up or spin down. It is a well-known fact in quantum mechanics that electrons tend to occupy the energy levels with the least possible energy. As the star nucleus shrinks to become a white dwarf, its volume decreases. Therefore, the available quantum states become less, given that N is proportionate to the volume. N is the available quantum states. As a result, electrons occupy higher energy levels. Higher energy implies greater velocity and momentum, thus higher kinetic energy in electrons. So the electrons create a pressure pushing outwards that outweighs gravity. Now let's move on to describing the fate of a star with a mass greater than 10 solar masses. The stars of this mass reach multiple states of fusion. At some point they reach the stage of thermonuclear fusion of iron, which is an endothermic reaction. This means that the heat needed to make the reaction happen is more than it gives off. So the star loses heat, thus it cannot balance gravity anymore. Consequently, gravity becomes dominant. The star collapses under its own gravity, thus the matter is compressed and electrons combine with protons, creating neutrons, while at the same time releasing neutrinos. At some point, matter cannot be compressed any further because of neutron degeneracy pressure. Neutrons as fermions can also have a degenerate motion. That is to say that neutrons as fermions exhibit a form of degenerate motion, as I just said. The other layers of the star collapse onto the extremely dense core, rebounding and being expelled at tremendous velocities in a supernova explosion. This is a type 2 supernova explosion, more specifically. So what this means is that, again, we have an instability between the core and the outer layers. So the core at sometimes stops shrinking because of neutron degeneracy pressure. But the outer layers are still shrinking, and sometimes they rebound on the core, and they are being expelled in outer space. This picture is a picture of the Crab Nebula that was first observed in 1054. Here's a visualization by NASA that shows how stars collapse into supernova explosions. And here we can see a more detailed visualization, again by NASA. The birth of a wonder of the universe. Then there are two possible endings for this neutron nucleus that are determined by its mass. If the core is less massive than 2 to 3 solar masses, then it will remain a neutron star, as predicted by the Tolman-Oppenheimer-Volkoff limit. This star balances the force of gravity with the degeneracy pressure of neutrons in its interior. This visualization shows the size of a neutron star compared to the city of San Francisco. Neutron stars are very small objects with a very small radius, when neutron degeneracy pressure is insufficient. However, if the neutron core is more massive than the TOV limit, the neutron degeneracy pressure will be insufficient to balance the force of gravity, so there will be nothing to prevent the gravitational collapse. So a black hole will be formed. At this point, let's recall what we mentioned in the beginning about compactness. According to Buchter's theorem, if the radius of an object is about 24.5% larger than the radius of an object of a black hole with the same mass as the object will inevitably collapse into a black hole. So we have an object, and this its radius must be smaller than 20.5% than the Schwarzschild radius of a black hole with the same mass as it. This is the equation that predicts this limit. So if the neutron core shrinks beyond this limit, we'll form a black hole, as I just said. Black holes are regions of spacetime where gravity is extremely strong. They form an event horizon, a mathematical surface that defines the boundary where the velocity needed to escape exceeds the speed of light. Since nothing can travel faster than light, as predicted by relativity, nothing can escape a black hole. General relativity predicts that at the center of black holes there is a space-time singularity, an anomaly of physics. A singularity is a point where every natural quantity is infinitely great. Also, it is a point in space-time where the equations of general relativity cannot be solved. So this implies that the laws of nature break down. Apart from the singularities, it is believed that black holes are just empty space. The scientific community and black holes. Black holes are undoubtedly very enigmatic creations of the universe. Many refers to them as creations of science fiction. The holy grail of the 21st century. One of the greatest challenges in the 21st century physics is unifying general relativity and quantum mechanics. So far, the two theories seem to be incompatible. String theory suggests that elementary particles are not points, but instead they are one-dimensional vibrating strings. Combining two theories that seem to be incompatible. Stephen Hawking first asserted that black holes are actually not black, but they emit thermal radiation. So as they emit the radiation, they slowly evaporate until they disappear. Once they completely evaporate, they leave nothing behind. So no information about what has fallen into black hole is left. Is left. The loss of information is called the information paradox. Quantum mechanics does not allow that. String theory seems to be able to solve the information paradox. Instead of describing the black hole only geometrically, we can see it as a creation of d branches and strings, the different ways in which the strings can oscillate and the branches can interact correspond to the microstates of a black hole. In this way, we can directly study the emission of particles from this d branch. Calculations show that the spectrum of the emission matches the thermal radiation predicted by classical theory. So, information is not lost, but instead encrypted in Hawking radiation. So, the existence of Hawking radiation suggests that we should not be looking at black holes from two opposite points of view. We need a theory that unifies them. Loop quantum gravity is a potential theory of everything.
Stavros, unfortunately, we have run out of time, and at 9 o'clock we should be closed. So
right.
Please, just take a couple of seconds to conclude your presentation. Thank you.
So here you can see my bibliography for this presentation. Thank you very much.
Thank you. Thank you. I'm sorry, but we really need to finish by 9. So, Yorgos Tsibon is next. Yorgos, okay, Yorgos. Please proceed.
Good evening, everyone. My name is George Sibonis. I'm 14 years old, and I'm a student of Ionidios Model High School. For as long as I remember myself, I have taken an interest in physics. Today, I'm going to walk you through Heisenberg's uncertainty principle. Now, before I start, the purpose of my presentation is not to torture you with advanced mathematics, but to help you truly visualize this impressive part of quantum mechanics. This is the structure of my presentation. I will briefly explain the uncertainty principle and then use some slides to discuss different aspects about it. Then I will follow up with the debates that are consequences of the uncertainty principle. And finally, I will conclude my presentation considering the philosophical impacts of the principle. For centuries, physics was a story of certainty. For Newton to Laplace, scientists believed that the universe was like a perfect machine. If you knew the position and velocity of every particle, you could predict the entire future with perfect accuracy. Nothing was left to chance. But in the 20th century, that vision began to collapse. With the birth of quantum mechanics, physicists discovered that at the smallest scales, nature is not deterministic, but uncertain. Today, I will take you through the story of this revolutionary idea. So we are going to have to skip the historical context due to the time pressure. Let's get right to the principle. Before we get to the principle, I want to talk a bit about the wave function, because I reference it in many of the following slides, and because, along with the uncertainty principle, they are the foundations of quantum mechanics. The most important point is that the wave function is the way to manage the tension between particles and waves in the wave-particle duality. Which are the tensions between particles and waves, you may ask? Particles have a location in space, while waves are spread out. Particles are indivisible, while waves are divisible. Quantum entities do not choose to be waves or particles. They are described by a mathematical object, the wave function, that encodes both aspects. The wave function has wave-like properties, such as wavelength and amplitude, representing momentum and position uncertainties. In this graph, we can see three different wave functions. The first function represents the function in which the momentum, the position, is more or less precise. The second one represents a function in which the momentum is more or less precise. The third one is a mix of the two images. Again, we have to consider that the function encodes both the particle and the wave nature of particles in a single mathematical entity. After explaining all of this, it is finally time for the simple mathematical formulation of the uncertainty principle. The uncertainty principle states that the product of the uncertainty position of a particle multiplied by its uncertainty momentum is equal or greater than the reduced Planck constant, h bar, divided by 2. Consequently, it is impossible to specify precisely and simultaneously both members of particular pairs of physical variables that describe the behavior of an atomic system of a particle. The greater the uncertainty in position is, the smaller the uncertainty momentum is, and vice versa. Now, for the more curious ones, the reduced Planck constant is just the Planck constant over 2 pi. The uncertainty principle can also be expressed as an approximation. As you can see, uncertainty position multiplied by the uncertainty momentum is approximately equal to the reduced Planck constant, known as h bar. By now, you may have gotten confused at this equation. How can it be simultaneously expressed as an approximation and an inequality, you may ask? In these kinds of equations, which describe the smallest scales of the microcosm, it is not so much the accuracy that matters, but the order of magnitude. As you can see, the reduced Planck constant is a very small parameter, around 10 to the negative 34 joules per second. We usually use the second form because in every physical system, the uncertainty product takes its lowest possible value in the ground state. In the ground state of most natural systems, the product is around h bar. Only in some specific circumstances, the product goes as low as h bar over 2. The term ground state just refers to the state of a natural system with a minimal energy, as described by the laws of thermodynamics. Since we have taken a glimpse of the uncertainty principle, I think it's now time to visualize using this great video I got from TED.
Momentum. To get a particle with both position and momentum, we need to mix the two pictures to make a graph that has waves, but only in a small area. How can we do this? By combining waves with different wavelengths, which means giving our quantum object some possibility of having different momenta. When we add two waves, we find that there are places where the peaks line up, making a bigger wave, and other places where the peaks of one fill in the valleys of the other. The result has regions where we see waves separated by regions of nothing at all. If we add a third wave, the regions where the waves cancel out get bigger, a fourth and they get bigger still, with the wavy regions becoming narrower. If we keep adding waves, we can make a wave packet with a clear wavelength in one small region. That's a quantum object, with both wave and particle nature. But to accomplish this, we had to lose certainty about both position and momentum. The position isn't restricted to a single point. There's a good probability of finding it within some range of the center of the wave packet. And we made the wave packet by adding lots of waves, which means there's some probability of finding it with a momentum corresponding to any one of those. Both position and momentum are now uncertain, and the uncertainties are connected. If you want to reduce the position uncertainty by making a smaller wave packet, you need to add more waves, which means a bigger momentum uncertainty. If you want to know the momentum better, you need a bigger wave packet, which means a bigger position uncertainty.
This is a very nice demonstration of repeatability. I hope it became much more clear to you. Now, another great way to visualize the uncertain position is by using a wave function. What you can see here is a periodic sine wave, which is the wave function of a particle. A periodic sine wave is a repeating pattern. As you can see, the wavelength of the wave is stable, and it stretches infinitely all throughout the x-axis. As we mentioned earlier, the wavelength correlates to the momentum of a particle and the amplitude to the uncertain position. In this wave function, we accurately know the momentum of the particle, since the wavelength is known as stable, but it stretches infinitely all throughout the x-axis, so the uncertain position is infinite. At this point, you might wonder, if everything is made out of quantum particles, why don't we see uncertainty in our everyday world? The answer lies in these simple equations. We already know that momentum is the product of the mass of a body times its velocity. We can play around with the equation, so it takes this second form. The uncertainty in position multiplied by the uncertainty in velocity is equal to the reduced Planck constant divided by the mass. And therefore, the greater the mass of a body, the smaller its product of uncertainty is. Also remember that the Planck constant is an incredibly small number, and it gets even smaller by dividing it with a mass. So the factors get smaller to satisfy the product. I will now demonstrate a practical example of the uncertainty principle on a macrocosmic body. Let's add an example with a grain of sand. Let's say that we know its position with an accuracy of 10 micrometers, a pretty realistic measurement, and its mass is around 10 milligrams. So now, using this formula, let's calculate its uncertainty in speed, which correlates to the uncertainty in momentum. We get that the uncertainty in speed is around 10 to the minus 23 meters per second, a very small number. 10 to the negative 23 meters is around 100 million times smaller than a proton. Therefore, we can conclude that the uncertainty principle is negligible in the macrocosm. Here you can see some artworks inspired by the uncertainty principle. Now, despite the fact that the principle is negligible in the macrocosm, it clearly wasn't negligible for some famous scientists, who obviously had some disagreements. Now it's time to talk about what I call the quantum schism. In the mid-1920s, quantum physics faced a split. Werner Heisenberg believed physics should only describe what we can actually measure. He developed matrix mechanics, a strange but powerful formalism that embraced probability but an uncertainty. Schrödinger, however, disagreed. He wanted a smooth, continuous picture of reality, a universe of waves evolving predictably through his famous wave equation. The clash was not just mathematical, but philosophical. He was studying against the most famous and emblematic physicist of his era, Einstein. Einstein rejected this very idea of quantum uncertainty, famously declaring that God does not play dice with the universe. Schrödinger was equally skeptical, and contrary to popular belief, he developed the cat experiment only to mock uncertainty and to show how absurd indeterminacy seemed. Even as Bohr, Born and Dirac wrestled with interpretation, Heisenberg stood his ground, stating that uncertainty is not a flaw in our knowledge, neither is it a measure of fault. It is a property of nature itself. This was not just a clash of equations, but a battle over the very meaning of reality. The battle is now over. Modern physics experiments confirm that Heisenberg was right. Let's leave history behind now. This is where it gets exciting. Let's move on to probably one of the most important implications of the uncertainty principle, atomic stability. As we earlier mentioned, natural systems tend to their ground state, the state with the least energy possible. Electrons inside the atom have both potential and kinetic energy. When an electron is far away from the nucleus, its potential energy increases and its kinetic energy decreases. When an electron is close to the nucleus, its potential energy decreases and its kinetic energy increases due to the increase of the uncertainty momentum. The average momentum is very high. Here, you can see three different theoretical models of the Bohr atomic model. In shape A, the radius of the orbit of the electron is very small. The electron comes very close to the nucleus, so the potential energy decreases. But in such a small region, the uncertainty position is small. Therefore, the uncertainty momentum is large, and therefore the average momentum are very large. And the kinetical energies become very large as well. The opposite happens with the second shape. In the third shape, the sums of the momentum is minimal. So the uncertainty principle dictates the ground state of the atom. Let's skip those next slides and get right to the end. For centuries, physicists believed in determinism, the idea that the universe is like a perfect clock. If you knew the position and velocity of every particle, you could in principle predict the entire future. Laplace even imagined a demon who knew every force and could predict the future. But in 1927, Heisenberg showed that nature doesn't allow this. His uncertainty principle tells us that we cannot simultaneously know the position and the momentum with infinite precision in the microcosm. This isn't a limitation of our instruments, it's a fundamental feature of reality. And that means something revolutionary. The future of the universe is not predetermined. It is governed by probabilities. Quantum mechanics mark the true end of determinism in physics. Thank you.
Thank you very much. Sorry that I did interrupt you, but the time is limited. Leon Gougoulias.
Hello, I'm Leon Gougoulias. I'm from Greece, and today I'm going to present to you my presentation about materials. What are quantum materials, though? They are materials that exhibit exotic behaviors, like entanglement, quantum interference, and topology. Unlike classical materials, the electrons can behave in many exotic ways. Some materials, for example, so you can understand how they actually use these behaviors is like that we can identify them in two different categories. First of all, we can identify them in the solids. In solids, we have the graphene, which is one of my favorite materials because it's a 2D material. Then we have the cuprates and the topological insulators. Some examples of some non-solids is the hydrogen sulfide, which under high pressure exhibits some very weird behaviors. Then we have the Bose-Einstein concentrators and Fermi gases. Some key quantum phenomena are quantum entanglement, in which two particles entangle together, and then when one changes state, the other one changes state accordingly. Then we have the superposition, in which a particle can have multiple states at the same time. Then we have the strong electron correlation, which basically says that electrons do not act independently but interact strongly. Then we have the topological order, which also says that quantum states depend on global symmetry and not on global geometry and not on local symmetry. Let's start with the first type of quantum materials, superconductivity. When a superconductor is cooled below its critical temperature, his resistance drops to zero. Superconductors use Cooper pairs, which I'm not going to get in detail to due to time constraints. But these pairs condense into a single quanta state, which basically lets the flow of energy without any losses. Then superconductors have the Meissner effect usually, which expels any magnetic field that they get from the current flow. Now, superconductors are, of course, the perfect conductors because they have zero, basically, resistance to any current flow. Their applications have been maglev trains, MRI machines, even quantum circuits. Then we have the topological insulators, which, in these materials, the electron spin is strongly linked to how it moves. The surface of the material forms special electronic states that cannot be easily destroyed by any bumps or impurities. If an electron tries to move in one way, its spin locks its direction. This means electrons on the surface move in well-defined paths and don't scatter easily. Now, mathematically, the electronic state has a topological property that is extremely hard or even impossible to change. And that's why the conductive surface is robust. Even if the material has scratches, dust, a broken surface, it still conducts, it still lets current flow. In normal metals, electrons, when moving, bump into atoms, and that creates resistance and heat. Here you can see the visualization of topological insulators, and their application is mainly on quantum computing and spintronics. Now, there are a lot of applications to quantum materials, like in quantum computing, when qubits usually use topological states, or for superconducting circuits, which, as I talked before, they are the perfect material for that. Then it's used also on energy tech, because superconductors, basically, because they have zero energy loss in transmission, it's, again, the perfect material. Then on spintronics, they manipulate speed instead of charge for efficient electronics. Then there is the use for sensors. Now, this morning, I thought I remembered to the time that I actually myself discovered of materials, this kind of materials. When I went to the Max Planck Institute close to the Technical University of Dresden. There they showed us how they do research on those materials. And they showed us some very recent innovations. So I decided to Google and find the most recent ones. First of all, I came across the Carmen nodal line metal, which is created by adding small amount of indium to a layered tantalum sulfur structure. This tiny change alters the crystal symmetry, leading to an unusual new electron behaviors. Then there is a not so new, but a lot of in the past was theorized about the QLEDs and the QRLEDs. And then the last one that I came across, it's a very important one, as a lot of people might understand that it's the most important. It's the symmetry in quantum materials, which they actually discovered about a nanosymmetric symmetry. That's it. I hope you enjoyed it. Thank you very much.
Thank you very much, Leon. Now let's move on to Sofia Mavrogiorgou. Sofia.
Hello everyone, and good evening from me too. I'm Sofia Mavrogiorgou, and I've been recently working on the applications of modern physics of quantum physics, to modern technology. So more specifically, we'll be taking a look on how computers work and what they are, but in order to do that, we first need to address some concepts of classical computers. Classical computers operate using bits. A bit is a storage of information that can store two values, 0 and 1. 0 signifies that in the transistor, which is in the processor of the computer, there is no voltage going through a specific space, while 1 means that we have electricity going through it. These bits create binary strings or sets of ones and zeros that express everything we can see in a computer, like letters, numbers, or even more complex things like colors, images, and even videos. These sets put together are translated into a low-level programming language, which is usually assembly in common computers, which is afterward converted into higher-level programming languages in order to be used more easily by people and so that they can create the software that they want to satisfy their needs. In order to manipulate bits, we use electronic circuits called logic gates. These are fundamental building blocks that are used to perform logical operations. And in order to do that, they have an input and output of ones and zeros, where the output is created using an algebraic function, which is fixed for each logic gate. As we can see in the picture, we have 8 main logic gates, but from there we can design any logic gate we want. And lastly, they use Boolean algebra in their representation, which is truth tables that show the inputs and outputs, as well as variables that are important for each logic gate. Quantum computers, as you might already know, are machines that are based on the laws of quantum physics and quantum mechanics, which in the past 2 decades have actually become real from the theory that used to exist. They're really important machines that are among the most compelling frontiers of quantum mechanics. This is because tasks that were previously considered impossible due to there really being big compilation time can be performed. These tasks are nearly or even impossible to be performed by classical computers. Quantum computers use quantum bits, in short, qubits. Qubits are vectors, so they are in superposition of values, meaning that they can exist in both 0 and 1 states simultaneously before they are measured. So, as we all know, vectors can also be notated in Dirac notation. So we have qubits with values of ket 0 and ket 1. Before the measurement, a qubit psi contains the ket 0 and ket 1, which are the basis states, which are multiplied by alpha and beta, which are complex probability amplitudes. Their squares give us the probabilities of either measuring 0 and 1 after the qubit collapses. We use amplitudes instead of probabilities because amplitudes are more easy to manipulate, and as the law of quantum physics interference allows us, we can either add them or cancel them, which is called constructive or destructive interference. Qubits are vectors, so they can be shown in a Bloch sphere. The north pole in the sphere is ket 0 after measurement, and the south pole ket 1, while in any other point the qubit is in superposition. On the surface of the sphere, we know the exact probability amplitude, so it's easier for us to manipulate and use the qubit for the computer. While as we go deeper and in the center of the sphere, we have a mixed state of the qubit that we cannot easily or manipulate, or it might be even impossible. Another property of quantum physics that qubits take advantage of is quantum entanglement, which is the really strong connection between qubits, which is of course stronger than the one classical bits have. And this is because no matter how far 2 qubits are from each other, if they are entangled, then the changes in the state of the one can affect the state of the other instantly. Here we have a system displaying quantum entanglement between 2 qubits. This is the addition of the qubits before measurement, which is multiplied by the probability amplitudes of having it. Here we have the example of equal superposition, which means that we have equal probabilities of having either ket 00 or ket 11. In order to manipulate quantum bits, we use simple unitary operations that are called quantum gates. Quantum gates are represented by matrices, so the gate action will be the multiplication of the qubits vector with the matrix, which will give us the final output. The sum of the quantum gates we create is called gate array and was used to call quantum network. Here we have an example of their representation. Here are some of the most used quantum gates. Some of them are also used in classical computers, but we have some like Poly-Y, Poly-Z, and Hadamard that are only in quantum computers. And in order to put them in action, we need to multiply the matrix of the vector of the qubit with the matrix of the gate. Now, we define noise as everything that causes a quantum computer to malfunction. Due to noise, information might get degraded and the quantum state might also be raised, or will certainly not end up where the computer programmer will expect. This is a property in quantum physics called decoherence, to which quantum computers are extremely sensitive. A lot of scientists are currently working on error correction algorithms that will fix errors in the hardware, but that's a process that will take really long to fix the errors because spreading information between qubits isn't as easy. So this is one of the problems we have in quantum computation. An overview of differences between the two computing models are the difference between bits and qubits, classic and quantum logic gates, the compilation time, which is of course faster in a supercomputer, and the way quantum bits and bits are entangled with each other, in which quantum bits use complex probability amplitudes. Lastly, something that was not mentioned above was that despite the fact that the computers have a built-in user interface, quantum computers are just machines, so in order to use them, we need to access integrated software online that is already available by large enterprises. In that software, though, it's only possible to combine quantum logic gates with each other. Here are the laws of quantum physics that are that a quantum computer takes advantage of and a qubit in order to function. And lastly, there are, as I already mentioned in the beginning, existing models already. A really famous one is Google's quantum processor, but there are also models like photon-based quantum computers. These models have no real utility for society. That's why in the integrated softwares online, it's not possible to actually construct our own programs. And it's important to say that quantum computers were only created to show how faster quantum physics can make a computer than classical physics, which is used in classical computers. Here is a table that shows how faster a quantum computer can be in relation to classical computers. Here, quantum computer using a specific quantum circuit that each one supports are compared with the on IBM's supercomputer, which is the fastest in the world. And it was estimated that the processing in the supercomputer will take 8.2 from 8.2 up to 48,000 years, although some of the facts were contradicted by IBM, and this created a chasm between the two enterprises. Lastly, as you might consider as well, quantum computers are the future of technology. So, with the physics, and also contribution to existing technologies, quantum computers will boost AI, LLMs, and machine learning, and will of course have a lot more effective algorithms, which will also construct error-correcting codes so that we can actually use quantum computers as tools. And in general, quantum computers will help produce better batteries, more effective medicines, and help the environmental problems that the world is facing. Thank you.
Thank you very much, Sofia. Thank you. Last but not least, Victor Yannikopoulos. Victor.
Κύριε Βουλιά, πού την έχετε αποθηκεύσει για την
Hello, my name is Victor for Communication and Autonomy Beyond the Heliosphere. So, here we see the structure. We start with bit to qubit, how Voyager communicates with Earth using the bit technology, anion qubits, and Neura in quantum computing, and cooling and sealing of anion qubits in the Stellar Probe mission. And before I start, a note. Anion qubits are currently at the of research and experimental simulations. So far, no practical implementation in fictional quantum computers has been achieved. This here should be as a future perspectives with a possible timeline for 2030. The goal is to highlight the potential role of this technology in the future missions. So, here at the first slide we see a century of quantum physics. We start with Planck, Einstein, Bohr, Heisenberg, and Schrödinger. We continue with Schrödinger's cat, followed by experimental kits, Bell, and Aspen. From the 80s, we see technologies such as laser, cryptography, and medical imaging. Today, we're in the second quantum revolution with quantum computers, AI, and pharmaceuticals. And the future brings also big questions. Quantum gravity, communication, and the quantum internet. From bit to qubit, so let's have a comparison between them. Bit has only two states, 0 or 1, and works with logical gate, all having a fixed result. But, on the other hand, qubits are in superposition of 0 and 1 at the same time, described mathematically as a combination of the two states. How Voyager communicates with Earth. Both Voyager 1 and 2 launched in 1977, and they still communicate with Earth. Bits, with the Deep Space Network in the USA, Spain, and Australia. They rely on a high-gain antenna, an X-band and S-band, but of about 22 hours on a way of 44 hours round trip. Recent restorations were made. Thrusters were reactivated and Voyager 2 was recovered through a so-called a signal from Earth. So, prepared you two videos for today. Let's start the first. There is a limit. an invincible boundary you cannot see, but you know it's there. It's the point where the power of the sun causes to ring, where its protective shield ends, and the vast, frozen, dark interstellar space begins. It's the end of our neighborhood in the universe, the beginning of the unknown. Until today, no mission was originally designed to create. Until today, the Voyager 1 and Voyager 2 mission years ago were designed to reach the Helios. And yet, with computers less powerful than a simple mobile phone, with technology that today seems almost primitive, the Voyager traveled, crossed the limits, and found themselves in interstellar space. An achievement of endurance and persistence. Without advanced systems, without sophisticated technological machinery. But now, this changes. For the first time, we are designing a spacecraft for its very first crew, with the purpose to leave the solar system and keep going. The interstellar probe is a dream becoming the mission that will go farther than human creations. Over 1,000 astronomical units, more than 150 billion kilometers from Earth. Lands between 2036 and 2040, 50 years and beyond, with no return. At its heart, it will not beat the technology of the past. No, it will beat with a pioneering system based on anion qubits, a type of topological quantum information so stable and resilient that it can operate in the harshest environment of the universe. These qubits will work alongside quantum artificial intelligence, not an AI as we know it today, but an entity that learns, adapts, and makes decisions on its own. A captain capable of traveling alone, without distractions from Earth, without signal, without help, for decades. NASA, in collaboration with MIT, Microsoft, the GPL and the APL are working on this technology, a technology that aims not only to take us farther, but to expand our boundaries. The interstellar probe is not just a mission, it is humanity's next step, proof that can create something unbound by time, space, all the limits we once thought insurmountable. This is interstellar probe, the first spacecraft designed to live and keep going. So, continue. What are anion qubits? Anion qubits in particles inserted two. The information is stored not in local states, but in topological braids. This topological nature makes them highly resistant to error and noise, essential for building stable information. So I'm going to give you an example. Wait a second. So you see here this rope? If I have it straight and I pull it, we see that it's changed easily. This is like classical qubits. The information can leave easily. They are resistant to noise. But if I tie a knot, we see that if I shake it or pull it or anything, the information is here. The knot is not removing. That's why, because they are protected. So, even in extreme condition, without this is not a billion anions. So, synergy between anion qubits and quantum AI. These slides show the synergy between AI and quantum qubits and anion qubits. Anions provide and fault-tolerant qubits, which quantum AI leverage for error corrections, simulations, and new algorithms. Applications from physics and chemistry to deep space, where the robustness of anions support reliable communication and real-time decision-making. So, how do anion qubits work? Classical particles are either boson or fermions, depending on how they behave when exchanged, but only in two-dimensional systems. A third type appears, anions. When they are breathing, as I gave the example before, the quantum state of the entire system changes. But this change depends on the path, not just the point. But why this matter for qubits? In anion qubits, information is not stored locally, like an electronic spins or range, but in the topology, in the breathing of multiple anions. This bridge acts like quantum logic gates, meaning computation are performed with the anions around each other. But anion qubits have some recruits. First of all, we need ultra-low temperature. Anions need around 10 to 12 to 20 millikelvin, close to absolute zero. Space itself provides a natural cooling background at 2.7 Kelvin, while advanced cryogenic and microcooling systems maintain this state reliable for long duration missions. Secondly, electromagnetic shielding. Beyond cooling, anions also require strong shielding from electromagnetic interference. Multilayer materials like copper and aluminum block radiation, while superconditioned magnetic shielding creates ultra-low noise zones, protecting qubits from space weather and internal disturbances. Okay, you see here this picture? These slides show how we cool and supercondition quantum circuit using liquid 3. So let's start from the left. As you can see there, we see the difference. Without helium-3, the circuit suffers from environmental noise. But when immersed in the liquid, thermal coupling improves and energy losses are reduced. Now let's look at the center. The circuit is placed inside the cooling chamber, where helium lowers the temperature to ultra-low level, as we can see there in the blue, down to 0.4 millikelvin. It's extremely close to absolute zero. And last, let's look at the right. We see how heat is removed and how the cooling keeps the system stable. Simply put, we immerse the circuit in an ultra-cold bath, so it can operate noise without maximum stability. Vibration isolation. Vibrations can destabilize quantum coherence. Qubit modules are mounted on vibration platforms to reduce effects from thrusters or structural shifts. Decoupling and damping technologies prevent structural or acoustic disturbances from reaching the quantum subsystem. And last but not least, we have environmental control. Environmental control is so important and so essential for the stability of anion qubits. Conditions like vacuum pressure and humidity are tightly regulated, while interstellar space provides an almost perfect Let's have a conclusion. The foundation structures of Planck and Einstein, the development of anion and quantum AI, were without this the creation of qubits from theory to applied technology. Topological qubits ensure stability, and fault tolerance enable large-scale computation with minimal errors. Quantum AI brings autonomy, optimization, time, data processing, with application ranging from complex systems simulating to interstellar space. The synergy of these technologies is not a scientific leap, but also a vital step ensuring humanity survival and persistence in space. Ultimately, every scientific advance is guided by the same principle: serving humanities and securing the future of our species. So, anion qubits, topological qubits, extremely stable and resilient. Space quantum AI, adapts and makes decisions, acts without direct instructions, real-time communication. In the particular solar Earth temporarily 1,000 kilometers of the sun. Now, Einstein was asked how he imagined the world. I do not know how, but I know that the fourth comes. Today, however, we can say something much clearer. We know how the third will be unfolded. It will be a war unlike any other in history. A war, both nuclear, weapons of the physical kind, and weapons of the digital kind. Unleashed from every molar stern, without limits, without breaks. And the fourth, it will not happen of caves, but because human species will no longer exist. Artificial intelligence will not wait. It will not need for humanity to end to take its place. It will have already ended the human era, much sooner than we can imagine. Life, however, always follows cycles. All forms of life are born, evolve, and fade away. Some last millions of years. Humanity's existence, as things are going, will have a tragical short cycle, but there is a hope. If we choose, we can set rules now, tomorrow, not when artificial intelligence defines a framework on its own, but us, humans, before it's too late. Otherwise, the end will be quiet, cold, and absolute, and perhaps in the absolute, a new species may emerge, a species that will no longer need us, a species that will continue where we have stopped. The time for action is now, before us.